So hi, my name is Tom. I'm a software engineer at Intel, and together with my team, we had the opportunity to work on some pretty interesting software with some pretty interesting hardware. But it's not really specific to the hardware. The software we do is hardware agnostic, so I'm not really going to talk about 3D-XPoint in particular. If you're interested, and I am not legally forbidden to answer your questions, then I probably can answer them after the talk. So let's leave all the 3D-XPoint specific questions until I'm finished. And since this is a C++ conference, I will be speaking about C++ only if I'm talking about the implementation. But before we start looking at the implementation, we have to give you some background, some basic knowledge about persistent memory and how to program it to persistent memory before you can actually appreciate all the cool work we've done. And frankly, now it's just because if I wanted to tell you everything, I'd need like 8 hours or 9 hours or probably more. So I got an hour, so I had to compact all the things I could. During all the talks that me or my colleagues or the architects have given, we noticed that different people understand the word model a bit differently. So it depends on who you're talking to. If you're talking to a hardware person, he's going to think, oh, he's going to be talking about some hardware-software interface that I can understand. And I'm not going to be talking about hardware-specific stuff. As I said, our library is totally hardware-agnostic, so no hardware-software stuff. The CPU hardware guys, they're going to say, or the kernel guys, they're going to think, oh, there's probably something about the instruction set architecture that's different and that's specific to the technology, and it's probably that. I will be mentioning some ISA because I have to give an overall picture, but it's not the topic of this talk. It's not the third meaning is also not the topic of this talk, but I'm going to go a little bit more in depth about what the OS exposes to the applications, to the user application, because that's necessary to get you starting using persistent memory in any form. But really what we'll be concentrating on is the programmer experience, because this is what matters. If you have a library and you want the library to be a success, so how do you measure that? By the number of users of your library, right? So if your library has a really difficult API, a big one that is hard to use, then it doesn't really matter how good your code is and what kind of magic it does. Nobody's going to use it because it's just not user-friendly. So we want to leverage what C++ has, all the features to make persistent memory programming, which if you saw it in C, how it looks, I'm not going to show that because I also like C as well as C++, and I don't want to diminish what C looks like. It's hard. It's really tedious. There's a lot of macros. You don't want to. C++ looks really, really better. So this is the mandatory slide. This is shown in every deck about persistent memory that I have seen. It depicts the programming model that was written by SNIA, which is the Storage and Networking Industry Association. There are a couple of companies which contributed to the standard, mainly Red Hat, Dell, HP, Intel, obviously, and Microsoft. So you had a bunch of really smart people in one room from totally different companies like Red Hat and Microsoft, and they said, and they didn't, argue with each other. They came to a consensus, and they produced a workable standard, which I think in its own is enough of an accomplishment, even without all the software and anything else. So that's the cool stuff. There's actually more than one way to program to persistent memory, but I will be concentrating on one part of the standard in specific, the one in the red rectangle, obviously. What this part of the model says is, if you've got a user space application up there and you have a persistent memory aware file system, in your OS, and you mmap a file or map view a file for those from Windows. And right now I have a question for you. How many of you have actually ever used the syscall mmap or map view a file? That's a lot more than I expected. Good job, because that's a really not a popular syscall. So you know what it does. It takes the contents of the file and puts it in your virtual address space of the process. So fine, I don't have to explain that. Great. So if the file system is persistent memory aware, then it allows you, when you mmap the file with a special flag called ODAX, DAX stands for direct access, you don't write to page cache. So every store or load you do actually from the device, which is kind of a half-truth. Well, I'll be explaining more about it later. So you don't quit page cache. You don't incur that penalty of the round trip to the kernel and back. And that is really important, because persistent memory is a dim form factor. It's really fast. So you don't want to go and ruin all that speed by going through the kernel, changing the context to the privileged mode and back again. It's not something you want to do. Now I said that you can write directly to the device without hitting page cache. That is of course not true, because you're going to hit the cache, the CPU cache, and the CPU cache is not persistent. If you have a power failure and your data is in the CPU cache, you've lost it. So in your application, you see that you wrote it, but it's not on the media. It's not in the DIMM. It's not persistent. So what you need to do is you need to flush the cache line which you've modified. You can do it from user space 3 ways. The old school way, so you can do a CL flush, which is a strong memory ordered instruction which flushes one cache line and sends it to the memory controller buffers. There are 2 new instructions. One of them is called CL flush opt, and it is not strong memory ordered, so you need a fencing instruction after it. The benefit of CL flush opt is that you can issue a number of those CL flush opts for a range of cache lines, and the CPU is free to do them in any order it likes to somehow optimize, and it in fact does optimize it, and it's like 10% improvement, I think, in flushing overall. So CL flush opt is a new instruction. There's also CLWB, so cache line cache flush write back, which is, as far as I know, and I'm probably right, is not implemented in any current processor, at least not on Intel, so probably not anywhere. What it does, it gives the hint to the CPU that, you know what, I'm probably going to be using that cache line right after I flush it. I need to flush it, but I probably will be fetching it again. So if you could, please do not invalidate it. And that's all it is. It's like if you'd be so nice, Mr. CPU, don't invalidate it. Of course, the CPU is free to do whatever it wants. If it wants to, it can invalidate it. There's also write back invalidate, which is only available in privileged mode, and it's a really heavy, really heavy instruction. What it does, it clobbers all your cache, all of it. It flushes the dirty cache lines, clobbers all your cache, and then issues a cycle for the memory controller buffers to be flushed as well. So it should not be abused, and as far as I know, the kernel guys are not abusing it because they are smart guys. So once you flush the cache line that you want to evict from the CPU cache, it hits the memory controller buffers. And historically, the memory controller buffers were not in the power failsafe domain. But all these smart guys and all the companies decided that it's going to be too hard to program if we have to manually flush the memory controller buffers. So there was an instruction for it. It got deprecated before it got implemented in the hardware. So right now, if you flush something to the memory controller, you can assume that it's safe. Even if the power failure occurs, the ADR, which stands for asynchronous DRAM refresh, and I don't know why, it just evicts it from the memory controller buffers. So you're safe. It will reach the DIMM. We've got to talk about its atomicity. The CPU, the only guarantee that I know of is that an 8-byte store is not going to be torn. So if you get an interruption, an 8-byte store will either result in the new data or the old data. Nothing different. But as far as I know, people rarely change their consistent state of application from one to another with just 8 bytes. Usually you want to do something more. You want to do like something like a string copy, for example. And a string copy is typically going to take more than 8 bytes. So what happens if you do a string copy and you want to, the PMEM persists there, you think of it as a CL flash. It's essentially what it does, and depending on the CPU and the features your CPU advertises. So you've string copied it, you're about to flash it, and then something happens. Anything. You take your kid to workday, right? You go to your data center and he yanks the cord out of the wall socket. The power goes down for the server. And it's like, it can happen, right? So what do you think? What will be the result if you power up the server again, you load your persistent part of the DIMM into your application, and what is the result of the string copy? Anybody have a wild guess? 1, 2, 3, 4, 5, none, any? Yeah, any of them. I don't know. There's this thing called cache pressure, and the CPU is free to evict any line of cache it sees necessary for that moment, because it's running out of L3 cache, so it decides that I'm gonna evict any line. And because this is not aligned, this is a character string, it's not aligned, it can cross cache line boundaries. Anything goes, actually. So this is a problem. This is probably the biggest problem of persistent memory programming, that it's low-level stuff that you have to worry about. And that is what we are here for, right? We, the software library developers, we want to make application developers happy. We want them to be able to program to persistent memory easily, naturally, not worrying about all those intricacies of the hardware. So we developed a library and some tools, which together with the language runtime and its features, provide you the necessary abstractions for you to easily, at least kind of easily, program to persistent memory. What we eventually want is something like this. So you've got a std vector, which everybody knows and appreciates. Is probably the best container there is in this std library. And with just substituting the allocator, you could potentially end up with persistent memory aware and transactional and really working without all the manual flashing and everything. It's something that I think is really neat, considering all the stuff that's going on behind the scenes. And actually, this is already there. I mean, we have in our GitHub repo, because I probably didn't mention, all of this is open source. It's on GitHub. You can download it, fork it, poke it with a stick, anything you want. You can correct it if something's wrong, do a pull request. If you find an issue, file an issue. We're open to any kind of contributions. So it's available. We have a modified version of libc++, and as far as I know, I haven't tested it extensively. I did some unit testing, and I think all of the containers work. They are slightly modified. Yeah. Yes.
You might be coming to this shortly, but I just want to make sure. This looks really simple for populating an empty vector into persistent memory.
Yes.
Do we have a slide about how we then load from persistent memory into
a
vector?
I think I don't have a slide for opening an existing pool, but I will be talking about it. I have a slide where we really have a pool handle, so I'll handle it when time's appropriate. So Yeah, it's there. It's backward compatible, so it didn't ruin any. It didn't ruin the ABI, the changes that we've made. Well, I'll be talking about it at the end. So, some naming rules. What is persistent memory? Sometimes called storage class memory or non-volatile memory. You gotta think of it as RAM because it kind of is DRAM. It's really fast. It's right up there with DRAM. It's like you've got NAND flash here. DRAM is here, so persistent memory is kind of depending on the technology, but it's kind of here. NVDIMNs, there's a type of persistent memory called NVDIMN, which is actually normal RAM with a battery and a NAND flash. So it gets dumped, the contents get dumped to a NAND flash. But the problem with that is that you have to have a really big battery and a lot of flash to have a large RAM DIMM, in fact. So they're not really popular because the capacity is small and they're pricey. So it's right there with DRAM speeds. It's just that DRAM is like Bill Murray in Groundhog Day. Each time he wakes up, it's a new day, right? It's the same. Oh, it's what happened? So it loses its all the values, and persistent memory doesn't, which is both a benefit and the curse, really, depending on how buggy your code is. And the other word I'll be using frequently is a pool. What I mean by pool is actually the contiguous blob of memory you have from mapping a file from persistent memory. That's like 90% of the use cases of pool, if I say it. The other 10% varies from context. We're going to go through with an example of a really, really simple, trivial queue. I just want to start with a volatile implementation and then step by step take you converting that queue example into a persistent memory aware implementation. So this is the queue entry. This the whole queue structure actually. I told you it was trivial. It's a singly linked list with share pointers, and we have a head and a tail because we want to push back and pop front. This is the only API that we'll be supporting. So we've got a push, which is trivial. You allocate, you update the pointers, and you're done. The pop is also similar. Some of you are probably gonna look at it and say, "Why are you throwing? Probably shouldn't throw." I know, maybe, yeah, I don't know. It's just an example, so deal with it. You can yell at me afterwards. There are three most important pillars. All of them are most important. I know that it's not correct, but it is. There are many things that constitute the library, and there are three things that are really, really important. Transactions are one of them. So what do you want to do if you want to make the API transactional? As easy as it goes. You just wrap the whole thing in a transaction because there's really nothing non-transactional in this because you do an allocation. Allocation has to be transactional. You can't leak memory in case of a power failure. And the only other things we're doing in this implementation is changing pointers. So you're changing the state. So you have to keep it under a transaction. This is in the form of a lambda function because I like lambda functions for this particular case. I like them generally. But in this particular case, they're wonderful because you see what's happening in the place you define it. So you read the code and it's easy to read. As you probably think, pop is not going to be really different. It's going to be the same thing. You're just going to wrap everything in a transaction. Some of you might say, well, you don't need to check the head pointer under a transaction, right? You're just reading data. You don't have to do it transactionally. Now imagine that you want to make this queue, probably not this queue because it's simple, but you want to make it multi-thread safe. Then the check actually has to be inside of the transaction because of locking, which I will explain later. There are a lot of intricacies, but we'll get through them. So the transactions, the decision we made is that we're going to do undo lock-based transactions, and that is because of visibility. if we decided to do redo log transactions, the changes would be made visible only if you decided to commit the transaction. And it's not really the natural way of writing algorithms, right? Your steps depend on one another, usually. So you want to write A equals 5, B equals 42, and C equals A plus B, and not do some roundabout computation for the redo logging. They have ACID-like properties. They are atomic, so either everything gets committed to persistent memory or none of it. We take care to make our data consistent, so the library data is consistent. What you do with your data in your algorithms, I don't care. It's your data. You have to care about your consistency yourself. The same goes to with isolation. We isolate the changes of the metadata of the library. We give you an entry point in the transaction so that you can isolate transactions from one another, but that's it. If you don't want to, or you have a bug, then it's just that. And durability, well, I mean, it's called persistent memory, right? If it wasn't durable, then it wouldn't really make much sense. Transactions can be nested. That was also a design decision that we made. Since they're undo log based transactions, unless you commit, everything gets rolled back. And the state is pristine, as if you never started a transaction. That includes allocations and deletions of data. And logs are held until the end of the transaction, which is important, and I will get back to that. So we have 3 types of transactions in the library. 2 of them are available in every C++11 compiled compiler. One of them is available only in C++17. End up. This is the simplest form of transaction, and I urge you not to use it. It's there because it was simple. We wanted a scope transaction, a manual transaction, but it has many issues. I'm going to explain the first line because I'm going to do it only once. I'm not going to talk about pool handles anymore. So this is an opaque pool handle. Obviously, you can open more than one pool, load more than one pool into your application. So you have to be able to discern them. This is the root object, and this partly answers your question because this is an open. So we are opening a persistent memory pool and mapping it into the address space. And there's this notion of a root object, and the root object, you have to think of the root object as like the root of the file system. So it's your handle to all the other objects, all your directories and files. So you start from there. You open a pool, it gets mapped into your memory, and all the objects are already there. Everything's there. And you've got to your handle. And then you just traverse the structure from there, and once you find your vector, it's going to have all the data. And you just use it as any normal vector you would.
I don't see the part that turns that vector into being a live object that the abstract machine knows about.
Okay, so
I've got a memory layout that has a vector in it.
Yes.
But I've not blessed that to now be a vector to the abstract machine that knows that that memory really is a live vector object.
You're going to treat it as a vector because you're going to have a pointer to it. So for all intents and purposes of your application, it's a live vector through pointer arithmetics. It's going to be a vector. You're just going to treat it as.
I'll pick this about offline. I think we're in undefined behavior territory, but I see a man over here who can hopefully put my mind at ease. So.
Okay. This is really a sanity check, because if you've got 2 pools and one of them has contents foo and the other has contents bar, and you try and open foo thinking that it's bar, then you shouldn't, because it's a totally different layout. So we do a sanity check so that you don't clobber your data. I mentioned the synchronization point, and it's here. It takes an arbitrary number of locks, different types of locks. preferably persistent memory resident logs, which we implemented, which have a special feature. And you just specify any number, and we will keep the log until the transaction ends. It's called manual for a reason, because you have to manually commit the transaction. By default, in the destructor, it aborts the transaction for security reasons and sanity reasons. And the reason it cannot be automatic is because you don't know why you're leaving scope. You don't know why the destructor has been called, at least not until C++17, where you do know why you're leaving scope. So that's why I'm saying that don't use manual transactions, unless you really have to. The logs drop here, as I said, which will be important in like 20 seconds. Maybe more, because I have to stop on this one. So the basic implementation of the library is in C. So all of us developers are C people. And literally nobody saw this. If you read it left from right, it says, transaction, get last transaction error. What else would it get if not a transaction error? It's from the transaction ID, right? It has to be through the transaction. It went through review, and everybody was like, perfect, that's the name we want to go with. And I'm looking at this, and no, this is terrible. But it's only 3 letters, right? It's only 3 characters. It's in the API. We've committed to it. We could deprecate it, put another one, and I don't think it's worth it. So it's probably gonna stay. And each time I give this presentation, I'm gonna have to say I'm sorry. There's another reason I don't like this, is because we cannot throw from the destructor of the scope transaction class. So the moment we leave scope, the transaction is like Schrödinger's cat. You have no idea. You don't know, did it commit? Did it abort? Unless you call this function and check, you have absolutely no idea. Do not use manual transactions. I can't repeat it more. It's gonna be on YouTube. People are gonna know, don't use the manual transactions. I've said all of this. This is just a recap slide. I'm not gonna go over it. I have many more slides. Automatic transactions, they are the cool kids, because C++17 fixed the std uncaught exception by adding an S. It's now std uncaught exceptions. And thanks to that, you know if you're leaving scope with an active exception. You know if it's whether it's stack unwinding or not. So now, and I think, I'm not like 100% sure because I did a pull request 2 days ago. I was looking at the slide and we still got the get last transaction error. And I was like, do we really need this? Does the only benefit from this be that we don't have to manually commit? Is that it? Can't we do better? And I think we can. I mentioned that logs drop here, which is really important because in the catch clause, the logs are no longer held. So if you have some cleanup that you gotta do, you have to manually relog. And that's a potential race condition, so yes?
So I'm just trying to understand the get last transaction error. Is that asking for the last transaction on the current thread?
Yes.
Or the last transaction on
on the current thread, yes. So is this still embarrassing? I don't know. If my pull request gets merged, and the pull request, what it does, it actually allows to throw an exception from the destructor of the automatic class. I know it's frowned upon. I know it's std terminate territory, but since we now know that we're leaving the scope because of an active exception, we can avoid triggering std terminate. And I'm like 95% sure. If someone gives me a reason why I shouldn't do that, I'll be happy to close the pull request. And I don't know, go into the corner and cry. Because I'm gonna say, don't use automatic transactions as well. Thankfully, again, recap, no time. Thankfully, we have something that I'm using in the queue example. And I like to call it lambda transactions. They're actually function transactions because they take a function object as the body of the transaction. But it's the best of all the worlds because it's not an object, it's a function call. So I can throw anything I want out of it. So I can notify the user if something happened that he has to handle. But there's one awkward thing. The synchronization point that I mentioned is implemented as a variadic template. So it has to be the last parameter of the function because you don't really have to specify any locks. So it looks like this. It's saying like, I'm gonna start the transaction and the body is gonna be a lambda function, which is gonna do some transactional work. Oh, and by the way, I'm gonna be locking 2 locks. I'd like to have that information up front if I'm reading code and not at the end. So it is what it is. Trade-offs all the way. But you don't really have to call this unless you want to know the specific error code of why the transaction failed. So while the C backing transaction failed. But you don't have to. You're going to get an exception. And if that's enough for you, then it's fine. So it takes a nested function object. It's automatic, available in C++11 and later. So it's got all the cool features, except the locking at the very end. Now the second most important, it's not going to have nearly as many slides. Is I like to call this the resides in persistent memory template, because that's what it means. This is our entry in the queue. This will get allocated, modified, deleted, depending on what the API call is. So what you want to do is snapshot the state of the object. The int value has to be somehow remembered by the transaction that in case you abort the transaction, you have to revert the state. You probably see where this is going. You need to do this. What P does is it overloads the assignment operator. And the assignment operator is a good trigger point because it probably means you're going to write something to it. So you're going to change the value. If you're going to change the value, then I inadvertently have to do a snapshot of the old value. That's not really the only thing it does. It also overloads a bunch of other operators so that if you had an int and now you have a P int, it has to behave the same. So that you don't have to change all the other implementation details of your application. And it was designed in a way that it's really a language feature because you don't have the overload operator dot. So if you want to store aggregate types in the P template, there is no convenient and natural way to access its members. There is a way through the more verbose API. But, then you'd have to change code, actually. And if it's okay with you, then it's fine. Then you can. It's just a bit harder. And now the persistent pointer. So this is the third and last most important part. We have our entry once again. As you can see, we've corrected the value, and now we still have the shared pointer. The shared pointer does not know anything about persistent state. But it does need to be snapshot. The value of the pointer needs to be snapshot because that also changes. It is part of the state of the queue entry. You probably know what the fix is because it's quite straightforward. You just change it to a persistent pointer. And since it's a persistent pointer, then it knows that it is in persistent memory and it is pointing to persistent memory. So it knows it has to be snapshot. It will snapshot itself if the value of the pointer changes. Easy. So how that works? Once you mmap, since almost all of you know what mmap does, mmap doesn't always map to the same address. So you can reload the same file into your application and get a different base address each and every time. So the persistent pointer is actually a base address. So it stores an offset within from the beginning of the pool. so that you have to recalculate your runtime address. It is a random yes.
So previously we had shared pointer that had ownership context over the pointed to object. Does the persistent smart pointer have ownership semantics as well? I'm not seeing those on the slide.
Yeah, so the question is, does the persistent pointer claim ownership of the memory? The answer is right now, no. And I'm going to argue about it, that it should. It's just that it's not really trivial. There are problems, but I don't like that it doesn't, and I think that it should. And the persistent pointers, it's got all the type defs necessary for it to be allocator friendly. So yes, the first bullet on the next slide does not manage object lifetime, and I don't like it. There are reasons for it, mainly because you'd have to treat differently stack persistent pointers, because you can have persistent pointers on the stack. The persistent pointer for the root object, for example, is a perfect is a perfect candidate for that. 99% of your root object pointers are going to be on stack. And the problem is that once that pointer goes out of scope, it triggers a deletion of the root object, which holds all the persistent pointers, all the references to all the other objects. And the domino just goes, and everything gets deallocated. And that's not the point of persistent memory, right? So we'd have to treat persistent pointers on stack differently than normal persistent pointers and implement reference counting like shared pointer does. And that's a runtime penalty. Probably not a negligible one, unfortunately. Maybe with some optimizations we could make it livable. But I think I'm going to show you how that affects the code, and I don't like it. I really don't like it, and I think we should implement reference counting for persistent pointers. It does manage the snapshotting. Question? Yes? No.
To me, it seems, let's say you have a pointer to pool, to a persistent pool. Seems there are two different ways of semantics of free. You might say, I don't need it anymore in my program, but it should still be in the persistent memory, or I don't need it in the persistent memory, it should be in this.
Yes, but you still have to do that manually somehow, or like policy-based pointers, or.
I think it's some kind of explicit decision that program does.
Maybe it's gonna mess with the allocation functions a little bit. Yeah, I think policy-based design in this case might cut it. That's a good point. Yes, thank you.
Is there a reason why there's only one pointer type? Like you replaced a shared pointer, but if you had like a unique pointer or a raw pointer, why don't you have like a persistent unique pointer, persistent shared pointer, persistent raw pointer, so on like that?
You probably could. I'm not saying you couldn't. You probably could.
Wouldn't that solve the issue that some pointers you don't want it to delete stuff it owns and some stuff?
No, because it's not really the type of the pointer that matters. It's the place that it resides in. That's the problem. Because if it is in the volatile part of your application, then it's gonna be always destroyed. The destructor is going to become, well, maybe not always if it abruptly ends, then not. But it's going to call the destructor, and it's the behavior of the destructor that has to change depending on whether it's a stack variable or if it's in persistent memory.
But wouldn't you have different types of? So if you have a pointer that's in like just in RAM, then you wouldn't have that be an owning pointer. It would just be a raw pointer into the persistent memory. But if the pointer was in persistent memory, you could use a different type. It doesn't seem like any one type needs to be the same. You could use different
Okay, so the question is if I could manage on stack pointers as volatile pointers into persistent memory. Maybe, yes. I think that would add additional complexity to your application, actually, because right now we just return you a persistent pointer to the root object, because it's fine if it's a persistent pointer, even if it's on stack. And then we'd have to return, depending on, because you can store a reference to the root object in persistent memory. It's totally fine. You can. So we'd have to return different types of pointers. Yeah, maybe it's an option. Yes, it's a viable option. Okay, I've got 20 minutes. Okay, I'm gonna dash through the rest. Sorry. Oh no, this is important. No polymorphic objects. The persistent pointer does not allow polymorphic objects, which probably kind of answers your artifact behavior question a little bit. Yeah, we don't allow polymorphic objects because there's no portable way to rebuild your vtables, because it's part of the ABI. It changes from compiler to compiler, architecture to architecture. We just decided we're banning polymorphic objects from the persistent pool at all. So sorry, it is what it is. So this is now our queue. It's fully persistent. It's got all the persistent pointers, and the data is also protected by the P template. Now the push is going to be really simple to fix. The only problem is that now we're allocating a shared pointer. Fixed. Now we are now allocating an object using our allocator and returning you a persistent pointer to the newly, not atomically, transactionally allocated object. The allocation is now part of the transaction, so if it aborts, the allocation never happened. It's fine. I'm giving you the pool for completeness so that you have a complete example of how this is implemented. And now the pop, and this is going to be embarrassing. And well, okay, you'll live only once. So I removed some code because it didn't fit in the slide. You're probably seeing. I know you're seeing this. We need a temporary value because of what's next to come. So you have to manually delete the object as it is right now, which is a bother because now you have to go through all your code and analyze where is it okay to remove your objects, to deallocate your objects. And it should be an anti-pattern, really. So that's why I advocated that it's probably a good idea to implement some sort of reference counting and manage the destruction, the lifetime of the objects held by the persistent pointers. And now you can update the head with the new value and it's fine. So this is the complete example. It's not like it's a lot of change. It's just one step too many than I would have wished. And I think we can fix that, and I think we need to fix that at one point or the other. So it's now a persistent memory friendly implementation of the queue we had at the beginning. The allocation functions are transactional. Make persistent looks exactly like make shared. It does a little bit differently, but the delete persistent call that we have is actually not something I'm fond of, and it doesn't have a counterpart in the standard library, right? You don't have a delete shared. It would be nasty. Okay. This is the thread synchronization isn't really all that interesting, except for the fact that these are persistent memory resident. So you can put these logs in persistent memory, and if you reopen the pool, you've got the old state of the it's not zero initialized or whatever is the initialization of the log in your current OS architecture or whatnot. So we have a scheme that reinitializes it automatically each time you reopen the pool. So if you use a log, then it gets magically reinitialized with the correct values, and it's fine. You can use it. But that's the only cool thing about these. Other than that, normal mutexes, shared mutexes, and so it was quite obvious that if we have a persistent pointer, we should have an allocator, which is standard library compliant. And we do, and there's really not much more that's interesting about it. It's normal standard library compliant allocator. Yes?
Since you said that it takes care of the OS remapping the addresses, is the size of the pointer on persistent memory still the same? Or?
So the question is whether they... Could you actually repeat it, because I don't think I...
So since you mentioned that the pointer addresses don't stay the same between, let's say, your process shuts down and you come back
Yeah.
to the process, is the size of the pointer just like a integer that you just adjusted back?
It's actually a little bit bigger than an integer, because it has to also have a reference to the pool. So it has to have a pool identifier and then an offset within that pool. So it's actually 16 bytes, which is 8 bytes more than we would want. Because if you do a, for example, if you want to do a data store with it, and you have to have a lot of pointers, then an additional 8 bytes. Normally it's just 8 bytes, but if you have to manage them and they take up more of your cache than you would actually want to, so it incurs a quite significant performance penalty, unfortunately, and we do not have a really good way around that yet. So it is bigger. So the containers and the question about undefined behavior. I'd like to hear more about it. Yeah. Gladly. So we have the pointer type implemented. We have the allocator implemented. The std containers are there for free, and they are maintained outside of our team, which is like the best plus ever. Because we don't have to bug fix everything. So it would be a sin not to consider using them, right? We could implement our own. Maybe the algorithms would work better, would be faster in persistent memory, because we could fine-tune them to the intricacies of persistent memory programming. Maybe, I don't know. The implementation in the standard library is quite cool, actually. So this is a std vector. I abbreviated all the insignificant stuff. So it's 3 pointers, right? I think it's the most common implementation. I haven't seen any other implementation in any standard library besides this 3-pointer. So it's a begin and an end and a maximum capacity. And since these pointers are actually persistent pointers, since we can pass our persistent memory allocator, then it works out of the box naturally. It's a different matter with, for example, std map, which is actually a red-black tree, at least in libc++. The problem with this is that it has a member data, which is of type bool. And as we've seen in the example of the queue, bool does not know anything about persistent memory. It doesn't know that it has to snapshot its value in a transactional context. So this will not be snapshot, and it's a problem. It's a problem we need to solve. But in this particular implementation, the node does not know anything about the allocator. And the allocator is actually the logical place to put information about what kind of memory you're allocating from. But it's not available here. You only have the void pointer, and you only know it because of the name, because it's a template. So we decided to inject the knowledge of the P template inside of the pointer, which is not ideal, but it was the simplest thing we could do, actually. So we decided to go with it. It is a proof of concept kind of thing, so... What it does, it defines, in the pointer trace, it defines an optional type def that if you don't define, then it falls back to a default type, and if you do, then it's going to be used. It's a nifty trick in the standard library. The rebind persistency type, which you can see up there, what it does, it takes your pointer, which at this moment is a void pointer, so it's a persistent pointer to void, rebinds it to a persistent pointer to bool, and extracts the persistency type. So right now, the bool type that you can see is actually P from bool. And that's exactly what we wanted, right? Now, the node is aware that it's going to be used in persistent memory context, and it has to snapshot its data. So we did a bunch of changes to all the containers, to all the data that was relevant. I think I got all of them. Some of them are static const data members, so it doesn't really matter, I think. I think it's fine. I didn't notice any ill behavior, and we tested it with a custom tool that we built, which I can also talk about offline. And we've got 10 minutes. It's the end. I'm gonna take questions now, and I don't know if I'll be able to answer all of them. But the known issues. There are these are just the ones that I could think of, like off the top of my head. Probably more, and I'm hoping you'll find more of them actually. I think the biggest one is that maybe it's not the biggest one. It's just a consideration you have to take into account while designing your application, because the data section of your or the BSS, the data and BSS sections they're not persistent memory resident. It would have to be like a loader change and an ELF standard change. So you have to bind your application, your executable with a pool file, so that the loader knows where to load the data section. It's a bother, right? It's way more changes than we want to. So all the data in the BSS, all your static data members or static variables, they're not going to be persistent. So don't rely on them being reloaded in the correct value if your application crashes. I'm gonna leave the versioning till the end. I already mentioned the vtables, so we don't support polymorphic types. We have no std string because the standard explicitly says that the type of the character held by the std basic string has to be a basic type. So a p template doesn't really cut it. It's not a basic type. So by default, std string cannot be used with our allocator. And there are no persistent references. I just put it there because we didn't do any core language changes, and we don't want to. That's a lot of fighting with the committee, I suppose. So if we don't have to, I mean, we get by without persistent references. So if we don't have to change the core language, it's fine. Don't do it. So back to the layout versioning. As far as I know, there is no such thing as layout versioning in the standard library. If I am mistaken, please tell me. And it is an issue because you compile your application with one version, then you recompile it with another, which could have a totally different layout. The implementation may be different. The layout of the data might be different. Any change might inadvertently destroy. Yes?
So with libc++, you can pick your ABI, either 1, 2, or 3.
So yes, you can pay the, but do you have a way to query the version of the ABI at compile time? No, at runtime actually.
At runtime, I think you can infer it.
If you can, then I'd like to hear more about it after the presentation, because that would solve like a non-existent problem right now. But maybe in the future it might be a problem if this actually gets used anywhere. So that was my last slide and some handy links. So thank you for coming. I hope I didn't bore you too much. Barely made it. So.
So two questions. One, would this library work with shared memory in a persistent to applications, but not necessarily the lifetime of the machine, so you could have transactional memory between processes?
You mean like TSX, transactional memory TSX, or?
I'm just saying if our system could allocate a shared memory partition,
yeah.
Could this library be used to manage that shared memory by multiple applications and do the same type of journaling and unrolling of journal writes and in a pseudo persistent memory?
So you'd like to just reuse the transactional part for your purposes?
Yeah.
all the algorithms are really persistent memory specific. So it's fine-tuned for persistent memory, so you might not get the performance you'd want. And the other thing is we don't support multiprocessing, but if you hacked into it, maybe I'm gonna say probably no. It's gonna probably be more work than it's worth.
Okay.
I think so.
And the second question is since the root object has to have knowledge of the beginning of all your data structures, would it be possible, perhaps only once they add reflections, you could do it automatically, but to like do garbage collect and just sweep through everything root knows how to find and to determine what memory is still alive and which memory isn't?
It's maybe. I really like the reflection parts, and I see like a multitude of applications for the meta classes. And could it be garbage collected? Garbage collection is actually a heavy thing. We have thought about it, and it's not easy to implement. And I don't really know if it's worth it. Maybe this is C++, so we're actually aiming more at performance probably than universal applications. I don't know if garbage collection.
Okay.
It's worth looking into, but I don't think we'll go there.
All right,
At
thanks.
least not in the near future. Thank you. Yeah.
I have a question about the snapshotting you were mentioning.
Yes.
That the situation you mentioned where the bool was the wrong type instead of the p bool.
Yeah.
I don't quite understand for primitive types what needs to be done. What does the p bool do that a bool doesn't do?
Okay, so what it does, because the bool has a value, right? It's a true or false, and once nodes are inserted, the color really matters if you're doing rebalancing. So during rebalancing, the value is going to change, and if it changes and the application crashes during the rebalancing, all the other things are going to be tracked by the transaction, except of the color. So you'd have an inconsistent state of the tree. The nodes would be back in the place before the rebalancing, for example, but the colors of the nodes would not be because the value was not snapshot in the transaction and was not reverted to the initial state.
I see. So the transaction has to keep track of every change that happens within that.
Yes.
I see.
If any object is in persistent memory and the state changes, then the transaction has to keep track of the values. Yes, of virtually everything. And as you can probably imagine, it has a performance penalty.
So I think the reflection stuff will help there too, especially the kind of stuff that Herb was talking about with being able to inject code.
Yes. That's one of the applications I was thinking. Yes, exactly. Thank you.
On your initial image, you only handled the right side of your image. In the middle, you said something like you can handle it like memory map file.
Yes.
Which I assume that's exactly the same way of working like you normally use a memory map file. How do you then compare it regarding performance with a normal SSD drive compared to non-volatile memory? Also regarding shareability, a memory map file you can access with two processes at the same time.
We don't allow. Yeah.
And what about this?
Okay, so we do not support multiprocessing. So we don't support because of the way our metadata of the library is organized. We don't have an easy way to support multiprocessing. That was a design decision we made like a long time ago. We just said that, okay, we're going to support multi-threading. I hope that's enough. And that's what we did. We are looking into making our library multi-process safe. It's just that it's not easy. It's a big rewrite of our code, and that's one thing. About the performance compared to SSDs. SSDs they are slower than persistent memory. The medium is slower. That's one thing. The other thing is that you have block access to an SSD, and here persistent memory is byte addressable, so the granularity is smaller. And to write to an SSD with an mmap file, you have to msync a whole page. So you have to send at least a 4K page, and if we're talking huge pages, a 2 meg or a gig page, which would be disastrous. And here you don't. You have a cache line. So depending on your algorithm, I'm going to say 90% of the time, persistent memory is going to be faster. there's the other 10% when it won't. Because all the algorithms we have now, they are actually fine-tuned to block storage. So we have to actually redesign everything for persistent memory.
Yep. Okay, thanks.
Do we have time for more questions? Or? I don't.
Yeah, we'll have that.
Yeah. Okay. Great.
Hi, I was curious about what CPUs actually support these instructions today. You kind of implied even Kaby Lake doesn't, so I was just curious if you could expand on that.
This is actually, you mentioned Kaby Lake. Kaby Lake is a client-side CPU. Everything I've talked here, this is data center stuff. It's not like you're gonna take a DIMM and put it in your PC. It's not gonna cut it. You have to have a server. So right now, there is no CPU which supports. I mean, there's no CPU that supports 3D-XPoint because 3D-XPoint is not out yet. But as far as other non-volatile memory like an NVDIMM, you just need CL-Flash, and CL-Flash has been there for ages. CL-Flash Opt, I think it's not commercially available yet. So you can't use CL-Flash Opt with off-the-shelf CPUs.
So yeah, the snapshotting problem's an interesting scenario. Have you looked into whether you can get hooks out of the transactional memory TS so that you don't need to create a P template, but would get a language support to say, within this transaction, I know I need to handle these snapshotting requirements?
No, I haven't, and I'd like to hear more about that.
It kind of looks like you are taking a lot of data structures that are written for like volatile memory and making them work for like non-volatile memory. What's the big motivation behind it? Because most people who rely on persistence, they don't use these data structures. No one puts STD string or STD vector on a
that's
persistent
fair.
medium. So what's the big motivation for doing all this stuff?
That is true. But as I said before, normally persistent store is not byte addressable. You don't have a small granularity. You have to think at least blocks of the medium supports, and if it's a MEMMAP file, then you have to think pages. So that's the main difference. And here you can use a vector. If you use the vector on an SSD, then it wouldn't make sense. If you wanted to transactionally add just one element, an int, you have to flash the whole page. You have to put all the 4K page, at least a 4K page, to the SSD, which doesn't make sense. That's why with persistent memory, you can actually you can leverage the stat vector or stat list, because you don't really have to invent your new. You can, it will probably be faster and work better, but you don't have to, and I think that's a big benefit.
Okay. The other question I had was, you had these cache line flushes. Is it possible at all for the cache line to be flashed even without you committing the transaction? Or is that?
Yes, it is. It will be flashed, but that's why you have the transactions for.
All right. So in that case, you roll back to the previous value.
Yes, you rewrite the new state that got flashed with the old data.
Even on a crash.
Yes. I mean, on the reboot.
Okay.
Not on a crash. Next time you load it, the moment you load, you open the pool, we go through all the transactions that have not been committed or have been committed but not finished, and we either finish them or roll them back.
I see. Another question?
Yeah.
Sorry, I have a lot of questions. So is there any possibility for the hardware to detect that it's actually dealing, like certain cache lines are dealing with persistent memory, and do something different about them instead of you guys doing like software style rollbacks and commits?
I don't think rollbacks and commits are not they're gonna stay. One thing you can do right now is mark a portion of the memory is non-cacheable, so that you wouldn't have to flash it. But then the CPU cache is there for a reason, because it's fast. So depending on the usage.
What happens, let's say for these cache lines, if I just set something that says that every write to this get flashed, like would it terribly affect?
Yeah, that would be marking as the region as non-cacheable. That would mean that it's not going to go to cache. It's just going to go straight to the memory controller. But then,
well, you can still cache it for reads, but
yeah, it's a penalty, right? Because you have to go to the memory controller, and the memory controller has to then put it on the DIM, and then it's a lot of time.
Okay.
I'm not saying it's not plausible, and I'm not saying that in some use cases it wouldn't actually be better than manual flushing. It's just that it's not general purpose, and we kind of want to go general purpose.
Okay, thanks.
So when you create the root, you were giving it just a file path. Do you have to have, does the OS, is there OS support necessary, or do you just need to have the NVMe drive on your box in order for that to be able to open and go through? Because you mentioned a special option that mmap needed to have, which none of the mmaps I know of have.
Okay, so first of all, an NVMe is a block device, so it's not persistent memory. No, it's just like, so that we have an understanding, it's not persistent memory. But the Linux mmap, it has a new flag since kernel, I don't know, 3.9 something, or 4. I think it's still in the 3 category. But it has a flag. It's called ODEX. I think you have to map it as shared memory, because otherwise it doesn't make sense. It goes to RAM. And what it does, it tells that that you want to have direct access, so you don't want to write to page cache. And as far as I know, both Microsoft and TFS has DAX support, and on Linux, ext4 and XFS do have, but it's it's a funny thing because we started off as a Linux library, and the Linux community decided that it's not really safe to flash from user space on ext4 and XFS because they don't have a synchronization point for their metadata. So it's not safe to flash from user space on XFS and ext4, but there's a workaround. The kernel guys implemented something called device DAX, and it's a character device which you can mmap and use flash from user space normally. Does that answer your?
It answers one part of it.
Yeah.
So the library does require OS support for this mmap option. There's not a way for it to talk directly and get this support.
No, I think. You don't really. I don't think I understand the question because if you don't have the ODEX, then you're going to hit page cache. If you hit page cache, then you have to msync. So we do support that. It's just that the pmempersist call is going to boil down to an msync, which will write the 4K or 2 meg or 1 gig, which is not ideal. So if you want performance, you're going to need to have persistent memory aware file system with the DAX extension or device DAX.
And with the direct addressable with your vector, do I understand it correctly that in this case, because of the characteristics of the persistent memory, that when you grow a vector, that you can just extend the addressed space, or do you actually have to go through the copy process of a memory vector?
You just go normal path, copy, and copy all the elements. There's no really way to grow. It's a standard allocator. It's standard compliance. So we didn't really do any changes to the vector itself. So if you run out of space, you have to reallocate the whole buffer and copy your existing data. Okay, thank you very much.